Hello and welcome to the Cool Planet webinar, Innovative Technologies for Reducing Scope 1 Emissions. Next. In today's presentation, we'll have three different areas of discussion. One by myself, Michael Smith. I'm a senior process engineer with Cool Planet. I'll be discussing low carbon fuel adoption and techniques for Scope 1 reduction using alternative fuels. Luca Manzi is a Grid Services Commercial Director, and he'll be discussing energy management and grid services as a technique for Scope 1 emission. Diana Ignatiuk will be discussing process optimization and the utilization of AI tools to help optimize your process and gain efficiencies through uh, through techniques and data analysis. And again, all three of these will contribute for Scope 1 emission reduction at your facilities. Next. One of the first aspects of fuel adoption is electrification of heat. Next. How does a business remove Scope 1 from their operations, where coal, oil, natural gas, and other fuel products like propane and diesel are the primary Scope 1 emitters by businesses? They're also the primary emitters by electrical production. But production from other than fossil fuels will generate, of course, less CO2 per kilowatt produced. Next. Continued investment in lower carbon alternatives to fossil fuels has continued to reduce the carbon intensity of electricity delivered to sites. This means a facility's Scope 2 emissions will be reduced over time. For example, the U.S. reduction in electrical production carbon intensity is 20% over 12 years, while electrical consumption remained nearly flat. Commercial industrial Scope 1 emissions depend on the functions of the business. Replacing these fuels with direct electrical heating for all of these functions is available, whether it's heating, boilers, or direct-fired furnaces. Even 13 years ago, however, in the UK, the cost per kilowatt of direct electrical heating was far more than other alternatives like biomass or heat pumps. The challenge here is to replace Scope 1 equipment with Scope 2 equipment while providing a payback on that investment. Next. So advanced options for Scope 1 fuel replacement. One of the first steps to take to electrify your business heating demands is to understand the temperature profile required in your processes. Many commercial and industrial processes operate at or below 90 degrees C. Outside of industrial heating, as indicated on the table, you have other areas of heating like building space heating at 22 C, domestic hot water at 50 C, or even sterilization processes at 75 C. And all of these processes don't require a combustion flame at 800 C or even steam at 180 C to do this job. Next. Industrial heat pumps technology has improved to be able to deliver hot water heat at 85 C efficiently and consistently. And there are newer systems under development to deliver hot water at warmer temperatures up to 120 C. These systems have an efficiency called coefficient of performance, or COP. And although it's dependent upon the installation and configuration, they can range from 2.5 to 6, meaning for every kilowatt of electricity delivered to the units, they deliver 2.5 to 6 kilowatts of heat output. But the units are typically closed loop, where the refrigeration is totally self-contained within the unit, and modular to the capacities and operational variations required by the customer. Next. One challenge to a new heat pump system is that the facility must now provide heat by means of a hot water utility instead of steam or direct-fired natural gas. This requires a new hot water distribution system, or repurposing and expanding an existing hot water system, which could reduce overall cost for this investment. Next. If your process requires warmer temperatures than hot water, then mechanical vapor recompression is available to create steam from vaporized hot water. An electrical boiler, of course, is an option again, but operating costs are higher than an MVR system. An MVR lifting water vapor from below atmospheric pressure at 80 C to 3-bar steam still has a COP of 4.0. So a fully combined system with a heat pump, providing hot water for lower temperatures, also providing water for vaporization, and then an MVR system to lift these water vapors to higher steam pressures can actually replace a boiler and utilize your existing steam distribution network. Only those processes requiring very hot process requirements would need either direct electrical heating or alternative fuel combustion. This is a change in thinking for utilities where you used to provide heat at the highest level possible and all users under it would utilize that heat. This is now lifting heat and grabbing it to the users sequentially up the temperature scale. Next. A case study exists, next, for industrial heat pumps that we've installed. An oilseed plant in Germany installed a heat pump to displace steam by heating air. The COP of the heat pump meant that heat from the electricity was cheaper than heat from the natural gas-derived steam. Next. A quick table of cost savings and other data indicates that this single heat pump had a fiscal savings of almost €500,000 per annum and a simple payback of 3.42 years, total investment of €1.63 million. Other fuels that are available other than electricity also offer an option for facilities. The existing facility locations typically never considered alternative fuel availability when they were built. So a survey of the surrounding environment is needed to adapt the facility to new sources of green energy. And electrical supply is ubiquitous, but there might be other sources of green energy available to the site. Okay. One of the first steps, of course, is solar. What available space is there in the facility property or adjacent properties for a solar array? You can also add battery storage as an option to increase the effectiveness of your solar installation. There's many resources available to determine the potential for a solar energy installation. And of course, local energy regulations need to be consulted to round out this opportunity. For fuel substitution, there are other two primary green alternatives, biomass or biogas. The advantage of these fuels is that their use replaces the utility equipment at the facility, but usually leaves all the downstream equipment in place, like the steam distribution network. Biomass burners, usually wood chips, require a facility location near a large timber source. Next. Biogas is produced from a variety of sources like landfills, wastewater treatment plants, dairy operations, or even cattle slaughterhouses, or organic-rich effluents from certain industries. For all biomass or biogas fuel supplies, there needs to be a reliable and consistent supply. So just like your natural gas line coming into the site, these supplies need to provide you with the energy in a reliable and consistent manner throughout the year. Next. In conclusion, a variety of green energy heating systems may be the best alternative to replace existing Scope 1 fuels. So evaluating the cost benefit of all alternative energy sources and electrical heat configurations to find the best fit for the facility is needed. And then a phased approach may also be available to install some systems first to partially offset Scope 1 while providing and adapting the installation for expansion to further offset Scope 1. And this approach will then allow the site to meet midterm goals while also meeting the glide slope for eventual net zero CO2 emissions from the site. I'll now pass you on to Luca Mansi.
Hi, everyone. I'll be talking through energy management through innovative technologies. So starting off, I suppose the premise of what is demand response and how does it work. So demand response is a means that the transmission operator can utilize large energy users, consumers to flex their demand in line with stresses on the transmission system. So historically, the way the system would work was when you had a lot of conventional generation, which admittedly we still do, you would be able to fluctuate that conventional generation in line with demand. But as more and more renewable energy or synchronous penetration, non-synchronous penetration is added to the system becomes, I wouldn't say not unstable, but a bit less predictable because it's harder to predict when wind is going to blow and when the sun is going to, well, there's going to be cloud cover for some. So the generation side of things isn't as predictable as it was previously. So demand response provides a lever for transmission operators to use and reduce that demand in line with, call it, grid stresses. And to facilitate that, there is compensation. So revenues can flow to sites such as which are like an insurance policy for the transmission system operator to be able to utilize this service, and sites can be compensated for that. Next. So as I said, the traditional energy system works both ways. So sites as well, large energy users and industrial sites as such would have had typical systems, less embedded generation. Embedded generation is the likes of your solar power or batteries, or even a backup generator could be classed as embedded generation. But historically and previously, a lot of that there wouldn't be as many of those what we would call flexible assets on those sites, and there would have been, as Mike covered, there would be different means to create heat and a less electrification across that entire site. Next slide. So the way the system is moving is that sites will have more and more flexible assets on their particular sites as they move to electrify and therefore reduce their Scope 1 emissions. Flexible assets, this covers kind of what we would class as flexible assets, but it's a very broad term. But examples would be battery storage systems, HVAC systems, heat pumps, EV chargers, anything with a large electrical load or a flexible electrical load that could be switched off for either long periods of time or short periods of time, or their operations can be moved to different parts of the day, can be classed as flexible within the grid services side of things. Next. So the way the system has changed, or the way sites are changing, not necessarily the system, but the way sites are changing means that they are getting more and more flexible assets. From what we've seen, they are getting more and more flexible assets, and they are becoming more and more complex. And all of this complexity that's now coming onto the site as sites electrify needs to be joined up to some extent, and the assets on site can be optimized, and they can talk to each other, and loads can be shifted, and import demands on the grid can now be shifted and better managed and used to, one, earn additional revenue and support electrification and reduction in Scope 1 emissions, and two, support the transmission system and transmission network, in that potentially less investment needs to be made into the transmission network in order so that, because sites are able to also flex their demand. And there are means to do that. So there are a number of software platforms. Cool Planet has one as an example, but you can utilize on-site storage, so it can flex on-site storage to adapt set points depending on market signals. You could utilize forecasting models as well, which is what Diana will go into, in order to optimize the site and understand when the best time is to charge a battery, as an example. Earn additional revenues, long-term revenues now for long-duration storage, or the additions of backup generation on that particular site. And you can also then refine your energy procurement strategy in line with the additional flexibility that you have, which could bring in a mix of hedging and pass-through tariffs, so you can reduce your volatility that you're open to through day-ahead tariffs, as an example, because you now have these flexible assets that can shave the peaks of energy. Next. So in conclusion, the demand response grid services side of the puzzle, if you will, is it can greatly support electrification of the site and offer a means and additional savings for the business case associated with electrifying a site and moving to and increasing scope 1 reduction. So that can be, as Mike had covered there, switching to fuels. We have a number of case studies where we've supported a number of sites in switching to HVO fuels from previously using diesel, adding secondary abatement system, selective catalytic reduction is what it would be called, to reduce emissions from generation. As I said previously, secure lucrative contracts and avail more complex tariffs. And the key to all of this is the digitalization of that site and the utilization of those flexible assets on those sites. Digitalization of a site then becomes a broader and necessary step in supporting the country and meeting green goals and optimizing the use of flexible assets. And on that, I will pass you over to Diana.
Thank you, Luca and Mike. Now I will go ahead and talk about process optimization, as Luca and Mike have covered CapEx solutions where investment goes in. I think that the first step into really looking at how we can reduce scope 1 emissions is by looking at what we can optimize with low cost or no cost solutions. You can go to the next slide, please. So one of the things that we use with really easy success and a lot of success are energy models. And we are basically using all the tools that are available on the market, from simple and basic ones that you for sure have access. Either Excel, either Google Sheets will have an extension for multilinear regression models. We also have capabilities, and you can buy these as well, like Aspen, JMP, and Python. And more recently, we started working with AI models. Now AI will go into Python and will reiterate models until it finds the best combination of all the different type of regressions that the AI can identify. Now, what is really important whenever we think about models and whatever type of tool we are using is the human experience, because in order for us to build the models, to identify what are the main influencers for these energy models and really validate the output of any type of system, we need human experience. We need subject matter experts that are able to look and validate that, yes, this is something meaningful for you. Next. Now, whenever we look at energy models, data granularity is really important. Here on the left-hand side, you have the same meter that we have modeled in 2 different ways. We modeled that into monthly chunks, and you can see that the model is the darker brown, the actual gas consumption or scope 1 consumption is in light yellow. You know, in the monthly view, the model doesn't sit on top of the actual meter, and we don't see all the influencers that are really changing the way that gas is being consumed on site. Whereas if we look at a daily view and even minute or more granular, if that is available, we will be able to create a more realistic curve and a more realistic dependency of what is actually influencing gas consumption and Scope 1 emissions altogether. Now, you may say, yeah, but there is a difference between monthly and daily because the monthly doesn't look at winter conditions, because maybe you see in the first part of the year that the model is really outside of the actual consumption. No, we generally, whenever we look at energy models, we look at least for 12 months to make sure that we are looking at all ambient conditions that are changing, all significant key units that you are producing at that moment, so that we can add as much variability in the model to be able to replicate the same consumption in the model. But why do we do this in the first place? So if you go to the next slide. We do this because with energy models, it's one thing to have one that is modeling the gas consumption and the Scope 1 emissions that we have on site. But it's another thing and another layer that we can have is to actually use that model to optimize and reduce gas consumption, therefore carbon emissions. Into the example that we have here, it is a real case study that we worked on. And we have created a steam model. Steam is consuming gas to be created, or a boiler is consuming gas to build steam. So this type of client that we worked on has a lot of steam consumption. And we looked at really identifying what is driving the gas consumption in this significant energy user that they have, to be able to identify how we can influence that steam consumption. And you can see into the pink boxes at the bottom, we have two models, but it's actually just one. In the first box, we have the steam consumption for this piece of equipment that we have on the screen. And you can see that the model, which is in blue, and the actual steam flow, it's in red, they actually follow the same pattern. So it means that the model is validated based on the meter that we have. Now, in the second pink box, you see that we have changed things a little bit, because together with people like Mike, process experts, we identified what is the best optimal condition that this piece of equipment can have based on historical performance and based on what the equipment is able to do, to work together with the site to reduce that energy consumption. And you can see into the chart that in the middle, there is a drop in the temperature that's actually influencing this consumption. And as the temperature drops, so does the steam consumption. And in this way, we help the client save around 922 tons of carbon in a year. Next. Now, yes, we can go into optimizing a piece of equipment, but we can also go into forecasting. And we are working with clients on forecasting the gas costs that they have if they buy, on the spot, or if they hedge their contracts. We can forecast how much they are going to consume in the next month, looking at, whatever is influencing their gas consumption. And also we are working with Flex, with Luca, on how what will be the electricity available on the grid, and how can we offset the gas consumption that the site has by using more electricity, or by using more solar panels, more batteries to charge the boilers, or to charge the heat pumps instead of gas. Next. In conclusion, the first thing that we do in optimization is actually look at low cost and no cost solutions. This is what we do in process optimization, is continuous improvement to its core. So this is really the first thing that we are doing. Then it's really important to have granular data, because granular data improves accuracy, and it's easier for then to know what is impacting the gas consumption altogether. We need subject matter experts to validate these models, no matter if they are created by AI through a platform, or through a simple tool. And by using these energy models that have been validated by the subject matter experts, we can forecast consumption and therefore emissions and cost. We can look at optimizing equipment. Thank you. I think that now we'll go into questions. I see the first question that we have is, can hydrogen be used as an alternative fuel?
I'll take that one. The use of hydrogen, although investment and production has been coming online, green hydrogen is the ultimate goal, and there will have to be a build out of infrastructure and production across the world, really, or in specific countries, before hydrogen becomes a viable alternative. One of the primary aspects on alternative fuels is reliability and consistent supply. So hydrogen will become a fuel to consider in the future, but at present, there's not a large enough green hydrogen infrastructure to be considered for any general site. There might be a specific site with a specific grant, but in general, it's not presently available as an alternative fuel to be a consistent and reliable supply.
Thank you, Mike. And the next question that we have is, what else can we do with energy models beside the one that you have mentioned? Yeah, I can definitely take that one. So we are using energy models to basically forecast the gas consumption to create performance for significant energy users. So for example, if we know what is the impact of different SKUs, which are single key units in manufacturing, then we'll be able to know through modeling what is the impact of each in the overall gas consumption. We also look at the optimization that I told you about, and there is another one that is really interesting, is creating virtual meters. So what these are actually calculations that work as a meter until you have capacity to buy the meter or until you can stop the production to install that piece of equipment. And we have been working with many clients, particularly where the install price is so high, wherever clients had significant energy users or they didn't know exactly what this piece of equipment is consuming. We work together with them on developing an energy model to estimate as good as possible what will this piece of equipment consume. Another question that we have is, can we create models without the meters and sensors? Yes, yes, we can create models without meters and sensors. We can look at ambient conditions. Generally, the colder outside, the more gas your facilities will be consuming. And another important factor that is production, if that is manufacturing. If you are not manufacturing, then we can look at working hours into the building, as well as the working schedule that you have to be able to create as realistic and close energy model as possible. I think that we'll stop for now. So thank you for staying with us. I hope that you got a lot of value from this meeting, and we'll be sending you the recording. And for any other questions that we didn't answer, we'll reach out to you by email.
Thank you.
Thank you.